Friday morning coffee. And if you're just joining, we'll be starting by 8:05 to give time for folks to join the meeting. We see people trying to join, and we want to have that number. I know some other people are joining on YouTube because we are live streaming this particular training. Thank you. All right, good morning once again. You're welcome to the intensive research training, popularly called the Friday morning coffee, hosted by the Central Office of Research and the Postgraduate College and the Postgraduate Student Association at Obafemi Awolowo University, Ile-Ife. And for today's session, we'll be looking at the technicalities of field experimentation and data analysis. And our facilitator today is Professor Richard Olutayo Akinwale. But before we dive into it, I'd like to call on Deputy Vice Chancellor, Research, Innovation and Development, Professor Kemi, to say a word or to open. Thank you. Over to you, Prof.
Thank you so much, Toby. Again, let me join Toby to welcome us to another edition of our Friday early morning research coffee. Again, let me welcome us all. I saw that people are still joining. Again, to appreciate all those who are working on this to bring this together, particularly the Director of the University Research Office, Professor Jide Odu. Thanks so much for all of your efforts and your work in sustaining this. Let me sincerely appreciate this our erudite scholar, Professor Richard Olutayo Akinwale, for agreeing to share, from his experience with us today on issues around technicalities of field experimentation and data analysis. So we'll be listening, I think, for the first time now to somebody who is from the Faculty of Agriculture to see, how we continue to share knowledge in terms of our methodological expertise. So, Prof, thank you so much for agreeing to share your experience with us today. So, without wasting time, I sincerely want to again welcome us all and to thank all those who have joined. Thanks so much, and I'm also looking forward to taking my 2 cubes of sugar from today's discussion. Thank you.
Thank you very much, Prof, for that very power-packed opening statement. I would like to call on the Director, University Research Office, Personal Professor Bawajo Odu, to introduce our facilitator for today. Over to you, Prof.
Yeah, thank you, Toby, for chaperoning this right from the beginning. So, and I want to also thank the DVC for the opening statements that he had made. I want to just do a brief introduction of Professor Richard Olutayo Akinwale, who is presenting to us this morning. The topic title, the title, Technicalities of Field Experimentation and Data Analysis. He's a professor of plant breeding and biometrics. Well, he's one of the top guys in our department that I've known for a long time, and then I know that we're in for a good time with the presentation this morning. And this is going to go for 2 presentations this week and probably next week. So I want to welcome Professor Olutayo Akinwale together with the Vice Chancellor, the Deputy Vice Chancellor, the way he has done this morning. So thank you.
Thank you very much. Yes.
Okay. Yeah.
Prof.
Can you just ask him to start?
Yes, we can. So, Professor Richard, Professor Akinwale, you can start, sir. Yes, sir. Over to you, sir.
Okay, thank you. Ladies and gentlemen, I want to say good day to everyone. And I want to say a word of thanks to the organizers of this seminar series. I am going to be presenting the seminar on the title Technicalities of Field Experimentation and Data Analysis. The outline of my presentation is as follows. Okay, so the outline of my presentation is as follows. We will be talking about the reasons for field experimentation, what it means and the reasons, the peculiar features of field experiments, some important terminologies in experimentations, principles of experimentation, and overview of experimental designs. Like it has been rightly said, I might not be able to finish all this within today's seminar. Maybe there is going to be a part 2 in the future. This presentation targets researchers, especially in the field of sciences and applied sciences. So those in social sciences and humanities might bear with us because we are targeting fields in sciences. So let's begin. Why field experimentation? An experiment is a type of research that studies the effect of an imposed treatment in a systematic manner. When a research is about imposing a treatment and we are studying the effect of that treatment, then we are talking about an experiment. Field provides a condition or provide conditions where several factors, climatic, edaphic factor, biotic and abiotic factors, human, diseases and pests, and so on, are interacting in a complex system where a plant or a crop grows. So no matter how promising the results of a laboratory experiment or a screenhouse experiment, the results is as good as what is confirmed or what is validated by what we have on the field. And this is because the users, the final users of the results of a research are actually practicing on the field, not really in the lab or in the screenhouse. They are there on the field, which are farmers. So in other words, results of screenhouse, greenhouse, laboratory studies, they are verified or they are validated by field experimentation. So thus, a successful layout of an experiment on the field requires taking into consideration these factors that are playing and interplaying under field conditions so that they do not influence the effect of applied treatment under study. Field experimentation has some peculiar features. The primary task of a researcher conducting an experiment under field condition are to properly manage the effect of numerous sources of variation, which are extraneous factors in the field that can confound the effect of the treatment under study. Factors that are not put into considerations that are there on the field, which might affect the results of the treatment that we are studying its effects or their effects, they are supposed to be properly managed and their effect minimized to the barest minimum so that the effect of the treatment that we are applying can be maximized or optimized. That is the goal of a researcher that is conducting an experiment in the field. Some of the extraneous factors in the field include soil heterogeneity, climatic variation, measuring devices. There could be variation due to measuring devices or the equipment that we're using on to take measurements. Farm inputs like fertilizers, like chemicals that we're applying to control insects and weeds. There could be sources of extraneous factors. Weeds, we can have different weeds on different plots in the field, which must be factored in. Pests and diseases, even field workers. If you don't manage your field workers very well, they will compound the effect of the treatment that you are applying. So all these extraneous factors have to be properly managed before the treatment that you are applying can make sense, or before the data you are collecting on the treatment you are applying can give you a worthy result. In order to handle these extraneous factors, there are two approaches. The first one is introducing blocking, and the second one is proper management practices. With these two approaches, those extraneous factors will be properly handled. To block effectively, the pattern of variation must be carefully observed. For soil variation, blocking must be made across rather than along the fertility gradient. These points, the above point, makes the use of completely randomized design grossly inappropriate for a field trial. We'll be talking more about this in the course of the presentation. Border rows and guard rows, they are peculiar features of a field experiment. And what they do is to help us to protect the experiment from rodents, from other pests that are not supposed to affect our experiments. They might also be used in creating necessary computations so that we can remove bias in the experimental field from one plot to another. The use of net row performs the same function as border row, where data are taken on the and outer rows serve as border rows. Guard rows are specifically planted to protect the experimental materials from emergent rodent attacks, as earlier alluded. We also have alleyway, which is also an important feature in a field experiment. All these features, they are to give us a kind of experiment that is free from extraneous factor that can destroy the whole experiment or that can make the result of the experiment.
Apologies. The presenter will be joining. We are facing heavy rainfall, and the presenter will be joining in minutes. Thank you very much. Once again, for those just joining, this is the intensive research training, popularly called the Friday morning research coffee, hosted by the Central Office of Research, the Postgraduate College, and Postgraduate Student Association at Obafemi Awolowo University, Ileife. We are currently having a presentation, but we are currently experiencing little technical issues. The presenter will be joining in a bit, so please stay tuned. Thank you.
Toby, are you able to reach the presenter?
Yes, we are working on it at the moment.
Yes, he's working on it. He's working on it. We are
Thank you.
together. What is it?
So while we wait for the presenter, I would like to say for previous sessions, they are live on our YouTube page. The link is in the chat box for us to utilize and explore. I mean, we have videos ranging from research design, ethics, and other previous editions.
He's back now. So maybe you can continue. Let him share the screen.
All right, Prof. Anita.
That's one of the challenges of technology. Okay.
All right, we can see your screen, Prof. Please go ahead, sir.
Okay. Sorry for the interruption. It's raining here, so the network went off. All right, I want to continue from where I stopped. I want to lay a foundation by explaining some terminologies that are peculiar to field experimentation and, of course, statistical analysis, so that we will be used to them when I am referring to them in the course of the presentation. So number one terminology is treatment. Treatment is the material being imposed on the subject and whose effect is to be studied or evaluated. So what you impose in your experimental design that you are studying its effects is called the treatment. Then we have factor. A factor of an experiment is a treatment with varying levels whose effects are to be studied. So a treatment becomes a factor of an experiment when it has varying levels, and the varying levels are to be discussed. So later when we are talking about analysis of variance, under sources of variation, you will have the factors listed and you test the effect of each factor using an error. Then we have a block. A block is a large area or several identical units receiving all or most of the treatments. So that is a block. Conditions within a block are expected to be uniform. When we establish a block, we expect as much as possible that the conditions within that block are uniform. And so if you apply a treatment in that block, you are expecting the variation that is due to that treatment alone in the block. That is, the block will not introduce any other effects. That is a block. Then we have a plot. A plot is the smallest unit of an experiment to which a treatment is applied. It is also called experimental unit. It is the smallest unit of an experiment. If we have 5 treatments and we are replicating the 5 treatments 4 times, it means we're going to have 20 plots or 20 experimental units. That is the meaning of plot in experimentation. Then we have experimental error. This is a measure of differences between 2 treatments treated alike. The measure of the differences that we observe within 2 treatments that is giving the same treatment, or 2 factors that is giving the same treatment. In other words, it is a variation that is recorded in an experiment that is not due to the treatment that is applied. the variation that is recorded in an experiment, which is not due to the treatment that is applied, that is experimental error. It is not really a mistake. It is called experimental error because any treatment that you impose on the fridge, the records are taken is not due to that treatment alone. There are extraneous factors, just like I said. And if the extraneous factors are minimized, then the effect of the treatment will be optimized. Then we have another terminology, which is interaction. This is the effect of a factor of an experiment on the other factor or factors in the same experiment. It is called an interaction. So let's talk about the principles of experimentation. Regardless of the type of experiment that you are considering, these three principles are germane. They are very, very important. The first is replication. In order to maintain consistency of results, experiment contains the same set of treatments are repeated on several plots or in time. To maintain consistency of results and to remove bias or decisions based on chances, experiments contain the same set of treatments. They are usually repeated. That repetition is what we term replication. Replication will be in time or in space. When the experiments are repeated on different plots at the same time, that is what we regard as a replication in time or in space. If it is done at the same time on different plots, it is regarded as replication in space. It will be location. If you carry out an experiment in Ife and you go to another location and carry it out the same time, that is replication in space. Then we have replication in time. That is if you don't have enough space to carry out your repetition or your replication and you just finished a rep, then the next time you plant the same thing and you repeat the same thing, that is replication in time. It could be in form of season. If you plant an experiment in rainy season and you repeat it in dry season, that is replication in time. So either replication in time or in space, it is replication. Another important factor or principles of experimentation is randomization. This refers to the allocation of treatments to plots without any bias. You allocate treatments to the experimental units, as I've earlier explained, without any bias. That is randomization. Both replication and randomization are put in place to reduce or to remove any element of chances or giving undue chance to one treatment over the other. Each unit has the same chance. That is, each plot has the same chance of receiving a particular treatment. So we established randomization to ensure that each unit has the same chance of receiving a particular treatment. So statistically, the randomization procedure allows elimination of bias and ensures the computation of valid sampling error. It helps to remove bias. The number of randomizations to be carried out depends on the experimental design that is used. If computer randomized design is used, it is only one randomization we are going to do. If you are using randomized complete blood design, the number of replicates that we use determines the number of randomization we are going to use for the set of treatments. So the third principle in field experimentation is introduction of a control or a local check. This is a standard unit in the experiment to which other treatments are compared. Any well-designed experiment, whether the field experiment or laboratory experiment or schoolhouse experiment, is supposed to have a standard for comparison. That standard is what we regard as control. The standard could be if you are studying the effect of a reagent, that should be a test tube. We are not applying that reagent and we are studying its effect. That is going to be the control. If you are carrying out a study on the field and you are applying, for instance, fertilizers or other treatment, that should be a plot where the fertilizer or other treatment you are applying will not be applied. So that is going to serve as a control. So any standard experiment or any experiment you can regard as a well-designed experiment must have these three principles put in place. If the principles are not put in place, then the experiment will not be regarded as a well-designed experiment. Now let's move to an overview of experimental designs. By definition, experimental design is the way or the manner in which treatments, that is, the factors of an experiment, are allocated to the experimental units or experimental plots. The manner or the way by which treatments are allocated or are applied to experimental units. The experimenter decides which individual unit is to receive which particular treatment according to a laid down procedure. So the choice of procedure will often determine the basic design to use. In principle, an experimental design is employed to minimize, if not remove, all sorts of bias that favors a treatment over the other treatment. So whenever an experimental design is used, we regard that experiment to be a well-designed or well-planned experiment. So the characteristics of a well-planned experiment, apart from the experimental designs, are as follows. A well-designed experiment must be as simple as possible. We must minimize systematic errors. Then it must have high degree of precision. Then it must have broad range of validity of conclusion. What are the factors that determine appropriate design to use? Number one, the type of experiments that were carried out. Types of experiments are on the basis of where the experiment is being conducted. Some experiments are conducted in the laboratory, so they are called laboratory experiments. Some are conducted in a greenhouse, and they are called greenhouse experiments. Some in the screenhouse, they are called screenhouse experiments, and then we have field experiments, which is what this presentation is all about. So depending on where the experiment is conducted, an experimental design is suitable. So if you are conducting an experiment in a laboratory, usually completely randomized design is suitable. And the reason is because all other factors are controlled. So you can say to a large extent that there is uniformity in the experimental space that you are using. And so the only variation will be due to the treatment that you are applying, which you are studying its effect. If you are carrying out your experiment in a greenhouse, likewise, you can consider completely randomized design. And this is because in a greenhouse, you control so many factors. It is only the treatment that you are studying its effect that that will introduce radiation. So completely randomized design is also good. But when you are considering a greenhouse study, from textbooks, they have recommended completely randomized design. But from experience, I have discovered that there are some greenhouses that you have variations which you need to lock against. There are greenhouses that the temperature variation within the greenhouse are not evenly distributed. The heat distribution in the greenhouse is not uniform. So in such greenhouses, it is going to be wrong to use completely randomized design because that source of heat will be a major factor that will introduce a variation that is going to compromise the effect of the treatment that you are applying. So for some greenhouse experiments, it is good to use completely randomized design. But in other cases, depending on the variation in the greenhouse, other designs might be used, which is going to capture the variations very well. An important example is a greenhouse study that I was involved in. The greenhouse was constructed adjacent to the faculty building. In the middle of the day, the faculty building cast a shadow on part of the greenhouse. And so the experiments that are laid close to where the shadow is cast will suffer because they will not be able to photosynthesize very well. Whereas those that are laid far from the building where there is no shadow, they will enjoy undue advantage of the sun. And so in such a greenhouse, it is going to be outrightly wrong to use completely randomized design. So for field experiments, completely randomized design is a no-no. It cannot be good because there are other sources of radiation that is not due to the treatment that you intend to study their effect. So that in one way affects the type of design to use. Objective of an experiment also plays a significant role in determining the type of design to use. If the objective of your experiment is to study interaction of two or more factors, then it is better to use a factorial arrangement and use an appropriate design than for you to carry out the experiment singly, considering the factors singly. So the objective of an experiment plays an important role in determining the appropriate experimental design to use. And the size of treatments. If the number of the levels of your treatments is sizable, is not too large, there are experimental designs that are suitable for that. But if the number of treatments is so large, some experimental designs are deficient. And so you have to consider some other experimental designs. Then the number of factors determines whether to use a simple one-factor experiment or to consider a factorial experiment using appropriate experimental design. Then the degree of precision that you require when you are having a factorial experiment also determines the experimental design to use. If you require the same precision on the 2 or 3 factors that you are considering, then the design you are going to use will be different from where you are more interested in a factor compared to other factors. So that also requires a different experimental design. Then the pattern of extraneous factors you observe on the field where the experiment is going to be conducted determines the experimental design to use. You might use randomized complete block design if the pattern of extraneous variation are not too much. They are simple that you can handle, that randomized complete block design can handle, then that could be used. But if the source of variation in that field is so numerous, you don't even know the direction, then you can use another design that we refer to as Latin square design. Number 7, the nature and the shape of the field of the experiment when you want to conduct the experiment also determines. If you are using a narrow field, the length is smaller than the breadth. The design you are going to use will be different from when the breadth is smaller than the length. It is very, very important to consider that shape of the field whenever you are determining the experimental design to use. Then the amount of resources and the facility available also plays an important role. The type of crop that you are evaluating, is it a tree crop or is it arable crops like maize, like cowpea? They also play an important factor in determining the appropriate experimental design. Lately, in the study that is conducted by me, I discovered that the type of traits or the nature of characteristics that you are considering in a study plays a significant role in the design of the experiment that you are going to use for the study. Let's briefly go to overview of experimental designs. From the viewpoint of hypothesis testing, there are 3 types of experiments. We have one we call a no-factor experiment. This is actually not regarded as an experiment because you are not imposing any factor, but you are just studying, like you are conducting a survey. The survey, you just want to gather information. It is a research, but not really an experiment. So we call it a no-factor experiment. Then we have a one-factor experiment, when you just have a factor that has several levels. And then we have a factorial experiment, where you have 2 or more factors that you are studying the effects of the main factors and their interactions. Experimental designs, especially for field. I am going to start from the first group of experimental design that we call complete block designs. There are several designs within this complete block design, and examples that we use: complete randomized design, which I have earlier talked about; randomized complete block design, when you have a factor. In the randomized complete block design, the assumption is that there is a variation in the experimental area, but that variation is simple and you can use block to control it. Then we have Latin square design for a factorial experiment. This assumes that there is a variation in the experimental design, but the pattern is not directional, it's a bit complex. So a replicate of block is partitioned into colon and row effects. Then we have another group of experimental design that we call the incomplete block design or the lattice designs. We roughly refer to them as randomized incomplete block design. So in this design handles large number of experiments. When you are considering 50, 100, 200 different treatments, then you consider an incomplete block design. So this becomes important when the leverage of a factor is becoming large, such that it is difficult to ensure uniformity within a block or within a replicate. So here a replicate is subdivided into smaller blocks, which are termed block within replicates. So there are two broad types of this incomplete block design, and they are balanced lattice design and partially balanced lattice design. The partially balanced lattice design are also referred to as alpha lattice design or rectangular lattice design. I am going to stop on this note. The next series, I will continue from here, and we are going to conclude on experimental design. Thank you for listening, and God bless.
Thank you very much, Prof, for taking us through that session. And I would like to ask if you have questions, please kindly use the chat box or use the raise hand icon. We'll recognize you and we'll call you. Again, I mean, there are claps in the audience already for the way Prof really broke down experimentation and how it works and the things to consider. So if you have questions, please use the raise hand icon and we can call you. And if you don't want to speak, you can use the chat box and we'll read out your questions for Prof to respond to. Thank you. And we're going to check YouTube too to see if we have questions from YouTube. We have viewers on YouTube, but no questions for now. Again, the floor is open for questions and comments from those joined. Oh, great. Prof, over to you, sir. Please feel free. Yes, sir.
Yeah, what I just want to say is that maybe when he presents something that like an experiment he has conducted over the years, that because he's a breeder, he's a pet breeder, he's a maize breeder, and then he has contributed into making the maize plant or the maize crop, available, and then also contributed to adding so much value to the maize crop, right from why he was at IIT as a student and then coming here. And he has also worked with so many, international researchers. And then they have so many maize products as the outcome of their research. So maybe he can come up with one of the experiments that that he was involved in that came up with maybe protein quality. So we have several maize varieties that you can definitely present to us as a part of the experiment that he conducted. So, and I think that by then we'll be able to ask very pointed questions so that I can answer those questions then. So somebody's raising up their hands too. I think somebody's raising up their hands. No, okay, I can't see anyone.
Thank you, Prof, for that intervention. Okay, I guess if we don't have questions for our presenter, and since the Professor suggested that we wait for a practical session where we can see the practical application of this session, we'd like to ask Professor Pawajo Odu to give us our closing remarks so we can give folks time to 7 minutes of the time. Thank you. Over to you, Prof.
Yeah. Thank you so much. I want to. Okay, Professor Kemi is raising his hand. So.
Yes.
Yeah, sure. Let him speak, please.
David, sir, please, over to you, sir.
Thank you so much. Thank you, Prof, for this beautiful presentation. I just want to make a remark. Listening to you again for me is so enriching. Because it also shows the strength, of multidisciplinary or interdisciplinary research. Because exactly this is also what we learn when we do experimental design, either for those of us in social sciences or those from clinical practice. I listen carefully. Even the choice of words that we use is just that, the application may be different. So I want to use it to urge some of us who are not from this particular field. But when he was talking, I was just speaking again. I mean, this, it's just about relating this, to crop science rather than, to other areas of in social sciences or for those who are also in clinical practice. But I think what we needed to do, please, let's take these slides, let's study it and see how we do each of these also in our own different field. Again, to appreciate Prof and to also encourage those who are not in this field to say exactly, it's just about applying this, in a different field. It's exactly what experimental design should be. So please read these slides and see how we again can also apply this, into our own discipline. Thank you so much.
Thank you very much, sir.
So thank you so much for this explanation, Shakinwale. We are grateful for giving us your time and then finding time to prepare and then come to this presentation. I want to say that we are honored that you agreed to. So thank you so much. And I want to thank everyone at Fanta to also be available this morning with your cup of coffee in your hands. Thank you so much. It's raining here. It's raining heavily. That was why we had that beach that came up. So, but we are able to overcome it. So thank you. So next week is another time that we would love to have you around for this presentation. I believe by then you will give us something that is practical, and then we'll see how in the study he has contributed to ensuring that there is food security in our world. Thank you so much. You're all welcome.
Thank you very much, Prof, for that. And we'd like to say for those asking for slides, this session is being live streamed on our YouTube. The link is in the chat for us to use. Please watch, like, and subscribe to our YouTube. And we'll meet here same time next week, Friday, for another session. And we look forward to seeing you. Thank you very much and have a good day. Over.